Consider an oscillator with natural frequency of oscillation as omega naught and damping parameter gamma, which might be due to the air drag or so. So in that condition, we know that oscillator has frequency omega 1, which is given as omega 1 square is equal to omega naught square minus gamma square by 4. Most of the time this gamma is small, so roughly omega 1 is nearly equal to omega naught. Now let us say that this oscillator is driven by an external force which is given by f naught cos omega t. So this driver is oscillating with frequency omega. So in this scenario we see interesting phenomena. As driver frequency increases, initially the amplitude of the oscillator increases, and at nearly omega is equal to omega naught we have a maximum displacement or maximum amplitude for the oscillator, which is called a resonance condition, which is marked by letter A in our graph. And when driver frequency is still increased, amplitude further decreases. So we have a maxima at omega is equal to omega naught. If driver frequency is below that, then also we have less amplitude, and if driver frequency is larger than this frequency, we also have smaller amplitude, and this is a resonance condition. Now if you look at closely the behavior of the oscillator, so when we have resonance frequency, then what we see on the left side top panel, the oscillator amplitude slowly increases in every cycle, and ultimately it goes to the maximum amplitude, and it continues there. On the other hand, if we drive the oscillator with other frequencies like at point B, then what we see is that initially there is increment and decrement of the amplitude, and later on it stabilizes to the driver frequency, and we see this type of behavior which is shown in graph B. So in today's experiment we will try to explore this behavior. Let us see. In our experiment, driving of this oscillator is going to be achieved by a motor. When we have larger potential given to the motor, then we will be having higher frequency of driving, and if we have a lesser potential across the motor, then we will be having a slower driving of the oscillator. Let me explain you the experimental arrangement. So here is the pendulum, here is the mass hanging here. It is connected to this point of pivot through a bicycle spoke. Here we have a small motor which is going to read the displacement from the mean position. It is hanged on this base which is nothing but one arm of the door closer, and this can oscillate about this mean position, so something like this. And there is another motor which is going to drive this oscillator, so that way we will be moving the point of suspension. And then there is this moving mechanism which is nothing but a rack dryer slab. So now these are connected to a data equation card which is basically going to tell us the voltage across the motor, that is going to tell us the displacement of the pendulum. And also we have got one power supply which is going to run the driver motor. So basically this is connected, this black and red, they are connected to this power supply, and that is going to drive the motor. And of course this data equation card is connected to the computer which will be showing us the displacement with time. So this is our arrangement. So now we start with low voltage. Let us say I set it for somewhere close to 4.1, 4.2. So that is the voltage. I start my program, and then I also start oscillations. we set the driver voltage to 4.2. You can see small oscillations, and the oscillator is following the driver. Now we set the voltage to higher, let us say about 5.2 we will be going. So it is 5.2. Now we run the program and start the driver. Now we will set further, let us say around 5.8 or 5.7. Let us see what happens here. So for this position, we run the program, we switch on the oscillator. Now we increase to further, let us say we keep around 6.2. Now let us go further. Let us say we will be going about 6.9 volt. I run my program. Now we go to higher, let us say 7.6 and see what happens. So here I stop to mean position, run the program and switch it back. Now let us see the response of the oscillator corresponding to different voltages, that means corresponding to different frequencies. So in this case we have kept the x-axis scale and y-axis scale similar so that it makes comparison easier. Let us see.